Welcome everyone to the 2023 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from Mark Peterson, the co-founder and vice president of advanced technology at Thea Technologies. Mark has over 40 patents and has been working in the optics industry for 25 years. Today he's joining us to discuss lenses for machine vision applications. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. Lastly, if you have any technical issues throughout this event, please log out and back in to rejoin the session. Mark, we appreciate you for taking the time to present the 2023 Vision Spectra Conference.
All right, thank you, Jacob. My name is Mark Peterson. I am the Vice President of Advanced Technologies at Thea Technologies, as Jacob said. Thea Technologies has been designing and selling lenses in the security and machine vision markets for 16 years. We do design and sales from our US headquarters, and we have a Japanese contract manufacturer who makes most of our lenses. Thea is most well known for our wide-angle lenses without distortion using our patented linear optical technology, and also for very compact, high-resolution motorized telephoto lenses. I'll discuss the latter in this presentation and how these can be used in machine vision applications. And then I'll also talk about our new calibrated versions of these lenses. As machine vision continues to make inroads into diverse applications, the utility of implementing machine learning and automation becomes ever more evident. Applications even as ancient as farming have seen the benefit from improved crop health monitoring using vision in drones and satellites. Traffic management, limited access city zones, and tolling have all benefited air quality and walkability of cities through machine vision ANPR applications. And inventory tracking and logistics have pushed machine vision to read smaller and smaller barcodes and process images faster. Although the majority of these applications can be set up with a fixed lens at a fixed focus distance during manufacturing or installation, there is a growing number of applications that can benefit from adjusting the focus or focal length after manufacturing. And adjusting might have limitations due to access to the lens. For instance, limitations may be due to packaging. This highly integrated vision system in a mobile robot may make it difficult to physically touch the lens after it is assembled. Or maybe there's a protective window that needs to be placed over the lens, such as these underwater robots that could prevent focus and field of view adjustment after the window is installed. Or the limitation could be external due to environmental issues such as traffic under a tolling system such as this. It's very expensive to stop traffic just to focus a lens on a gantry, and arranging for work zone traffic control is an external limitation. Or the lens could be used in a mobile system that can be moved around to look at objects at different distances, allowing the user to access the lens for any focus adjustment, may introduce a source of uncontrolled error because the lens may be adjusted incorrectly. So one solution to all these issues of limited access is to use a motorized lens. The lens, with motors to control the focal length and focus groups inside, it's possible to remotely and automatically change these without giving the user any physical access to the lens. An embedded computer or even a microcontroller can adjust the lens for optimum performance and field of view. So here's an example of a zoom lens used in an SLR or a movie camera. This allows the focal length to be changed without any effect on the focus of the image. So they have completely synchronized focus and focal length movements. For this type of lens, once the focus is set to a particular object distance, then the focal length can be changed without the subject going out of focus. This requires several moving groups and cam barrels to keep all the groups moving in the right synchronization. This type of lens is rather expensive and has some other compromises such as limited aperture sizes that must be balanced during the design of the lens. So in this animation, you can see that the three moving zoom groups, they're moving in synchronization, but they don't all move along the same paths. So the paths of each group is controlled by a cam with different shaped spiral grooves. This allows the lens to change the focal length without changing the focus position, focus object distance. Similarly, the first two elements in this group, in this lens, will change the focus without changing the zoom of the, or field of view of the object. These type of lenses are complicated and very difficult to design and manufacture. The most popular type of moving focal length and focus lens for machine vision is a varifocal lens. In this type of lens, there are still internal moving groups for focus and zoom, but they're not linked together. So once the focal length is changed, the focus group must also be changed for the object to remain in focus, even though it's at the same object distance. This video shows that first of all, the focal length is changed, but then the focus group must also be moved to get the object back in focus. This separation of focus and zoom allows lower cost of the lens and performance improvements, such as faster f-number. For example, Thea offers the motorized 12 to 50 millimeter varifocal called the TL1250. That's only 65 millimeters long. And it's f1.8 at the wide 12 millimeter focal length, going down to f2.2 at 50 millimeters. This is a very compact telephoto varifocal lens, and it collects a lot of light because of the fast f-number, making it good for outdoor applications where these are light-starved applications with uncontrolled illumination. These applications may need to work on cloudy or rainy days or even at night. This lens is used in many applications. One of the largest markets is intelligent traffic systems and tolling and other ANPR vision systems. These are generally large installations involving many cameras, sensors, and barriers that must be installed on site with minimal disruption to any existing traffic. Traffic is diverted while the gantries and cameras are quickly and efficiently installed over the road, often at night when there's less traffic. And the cameras and the infrastructure is installed before anything is hooked up to the main traffic control network. So the focus position of each lens cannot be verified during installation. Many of these systems use motorized varifocal lenses so that everything, once connected to the main system, the installer doesn't have to put up these cones to divert traffic again just to focus the lenses. The image can be optimized during the day when there's lots of light, and most importantly, it can be optimized remotely. So the field of view and the focus position of each lens can be verified. Although focus and zoom motors for this application are generally only used once during the setup, these lenses are a very cost-effective and safer solution compared to dealing with the general public driving through a traffic-controlled work zone. Another application is the use in a mobile speed camera, where the camera can be mounted at any location and any distance from a desired target point. The person setting up the camera should be able to adjust the field of view and the focus for the object distance for different objects. And because in the case of these speed cameras, the camera could be thrown into the back of a police car, it should have a very robust and fully enclosed outer case so as not to damage the lens or any delicate components. And so allowing any physical access to the lens could reduce the robustness of the system. In this case, a motorized lens not only allows the user to remotely adjust the lens without any physical access, but it can also or use as evidence. An application where the lens is highly integrated and may be difficult to access is a mobile robot. In an underwater robot especially, the lens should be protected in a sealed air environment. This requires a very tight sealing of everything and not allowing access to the lens after it's all been assembled. The underwater robot in the upper right is from a Cornell University team, and it was used in a robotics sub competition. In this case, they use 2 lenses from Thea for stereo vision for their navigation. In the other images below, these are from the NOAA Deep Sea Discoverer. The field of view and focus distance can be adjusted with an onboard computer to optimize the underwater image. The lens could be set for a large field of view when searching for deep sea creatures, as seen on the left. And then the focus and focal length can be adjusted to zoom into something interesting. These images show the ghost octopus, which was newly discovered in 2016. This application could use multiple cameras at different fields of view, but a motorized lens with a variable field of view offers more flexibility. There are many other applications where the environment requires that the user cannot access the lens, but they still want to optimize the field of view or the object distance, the focus distance. These motorized lenses will typically have stepper motors for the focus and zoom control. The motors can be controlled by a embedded computer or even a microcontroller. And the multiple moving lens group inside the lens must move in a well-defined relationship for the lens to achieve best focus. This is controlled by several cams in the case of a zoom lens, but in a varifocal lens, the zoom and focus lens groups are controlled with separate stepper motors, which have the defined relationship between the focus motor step position and the zoom motor step position. As you can see here, the blue curve shows the focus motor step versus zoom motor step. It's not a linear curve, but it is a well-defined curve. And in sophisticated systems, these 2 movements can be synchronized electronically so that the object can remain in focus regardless of the focal length, making this a simulated zoom lens. So there are many constraints when the optical designer is designing a lens, and because the primary function of the lens is to create a good image, the optical parameters will usually receive more weight in the merit function than the mechanical parameters, such as the focus motor and zoom motor actual steps, absolute steps, and their relationship between the two. So this looser tolerance on the motor position results in a variation from lens to lens. As a consequence, there is no universal correlation between the focus motor step and the zoom motor step number to guarantee that an image is in focus, especially when there's a large number of steps for focus and zoom motors, which implies a very high resolution lens. Thea Technologies TL1250 motorized lenses have about 3,000 steps for zoom and 8,000 steps for the full focus range. The theoretical curve for focus zoom tracking is shown. There's a large variation in the focus motor step position, but you can see these 4 different lines are very similar, and it's a similar curve with slight variation from lens to lens. So if we look at the 50 millimeter telephoto side where the zoom motor step is 0, that's on the left side of this graph, you can see that the focus motor step difference can be as much as plus or minus 300 steps from the lens to the design value. That's it's a very large number of steps. Although nearly 8,000 steps is available for focus, As I showed in the previous plot, the range is actually pretty tight. And so this plus or minus 300 step variation is a large difference. So in the case, if you set zoom lens 1 to the design value and zoom lens 2 to the design value, they may not be in focus based on just a theoretical position. But with some effort, you should be able to get both of these lenses into the highest focus position, the best focus position, to within about plus or minus 20 steps for the highest position image, as shown on the right. Similarly, this focus zoom curve is a function of object distance and is also variable from lens to lens. So when changing the focus from infinite object distance to 2.5 meters, for example, the focus may need to move 600 steps at a focal length of 30, which is approximately zoom step 1000. But a different lens might move only 500 steps for the same object distance change. This variation in itself is much greater than the plus or minus 20 steps, and it must be added on top of the lens to lens variation just for the focus at infinity. So you can see that applying a theoretical curve may not give you the best focus performance and will result in an image that's most assuredly out of focus. So although this focus zoom curve is highly variable, it's due to manufacturing tolerances in the lens. And without any individual lens calibration, the best focus will have to be found using an autofocus routine after each focal length adjustment. And without the knowledge of the direction or distance away from the design curve, the autofocus could take some time. So a well-characterized focus zoom curve is very beneficial in this case. It can speed up the autofocus routine by letting the user know approximately where to find the best focus motor step number for any focal length. Because of the variability, each lens should be calibrated individually to find the best focus zoom curve and make the setting much more precise and much faster. Thea has calibrated lenses such as the TL1250P-CAL, which is the same 12 to 50 millimeter varifocal lens I described earlier, but it's calibrated at the factory. So the end user and integrator has access to this focus zoom curve calibration for each lens individually, as well as other data frames such as distortion or focal length versus zoom step number. So this focus zoom tracking curve is one data frame where the calibration data for individual lenses may be very beneficial by speeding up the autofocus, the focusing position for best focus. Due to limitations of testing and data storage, it's not possible to test all combinations of the focal length and object distance for the zoom focus curve, for example. And so some interpolation will be required to access any point in the 3 to 4 dimensional data space. One efficient way is to save the data for calibrated lenses in a polynomial curve that is fit to the measured data, and just store the coefficients of the equation with control points defined for the different curves. For this focus zoom curve, there can be many curves relating focus step number to zoom step number for different object distances. And so in this case, the object distance will be the control point, making this a three-dimensional data set. For some calibrated data frames, there may be more than one control point. For example, relative illumination will depend both on focal length and the aperture opening. So that would be a 4-dimensional data frame. But for the focus zoom tracking curve shown here, you can see that there are the two control points, one control point with two different values for focus at infinity and focus at 5 meters. And because of the inverse relationship of object distance and to focal length, as shown in the thin lens equation, the control point is chosen as 1,000 over the object distance. So this makes the interpolation much easier because it's not an inverse function. For these calibration data frames, most optical parameters vary smoothly based on the chosen control parameters. And this makes a simple linear or cubic interpolation possible for finding any data within the entire data space. So you can see there is a small variation from the coefficients between the control point 0, which is infinity, and control point 200, which is 5 meters object distance. But anywhere between, it should be a simple interpolation to find the position of the focus motor. So say, for example, the user wants to set up a system at 50 millimeter focal length, and the object is 10 meters away, but the calibration data only exists at infinity and 5 meters. They can easily interpolate to find the expected focus motor position. The zoom motor step position is 0, and at the maximum focal length of 50 millimeters. And so the focus motor can be calculated from the polynomial coefficients and then just a simple linear interpolation to find the expected focus motor step position between those two. You can see that if the control point was just the simple object distance, doing interpolation between 5 meter and infinity would be challenging and not well defined. So taking this inverse relationship for the control point makes it possible to do this interpolation. And then once you know the focus motor step position, the expected step position for that lens, you can easily go there and do a fine focus adjustment if it's not quite exactly what you need, but you'll know how to get there quickly, and you won't waste some time just searching a large space. So Thea's calibrated lenses have individual data files that contain the focus zoom curve data as well as other calibrated data frames. And these files are presented in a human and machine readable JSON format that will be available for the user or integrator to download from our cloud database at any time. The data will include some basic information about the lens, such as serial number, calibration date, and limits, as shown at the top of this data structure. And then there will be calibrated data frames, such as focus zoom tracking data, shown here under the key tracking. Focus zoom tracking data shows focus motor step on the y-axis and zoom motor step on the x-axis. And the control points are CP1, and these are defined as 1,000 over the object distance. So you can see the polynomials for the two of the control points are listed here. And there are other calibrated data frames such as focal length, distortion, aperture size, all included in the same file. Some of these are design values, but many of them are calibrated on an individual lens-to-lens basis. So as you can see, there are a growing number of applications that require motorized lenses. These motorized lenses can be used for setup when safety or accessibility warrants it, or during normal use when controlled by a embedded computer and you want the flexibility of a variable focus or focal length. Many applications can benefit from this flexibility, but this does come with some challenges for achieving accurate focus. And these challenges can be overcome by calibrating each lens individually and applying a calibrated data file during operation, so that the integrator or end user doesn't have to do their own calibration. Thea Technologies offers individually characterized and calibrated lenses with a computer readable data format to enable this enhanced image performance and faster image processing speed. So again, my name is Mark Peterson, and thank you for the presentation.
Thank you so much, Mark, for joining us and presenting on both motorized and calibrated lenses. I do have a question for you, but before I get to that, I just want to remind everyone in the audience real quick. If you haven't already, you can type your questions and comments into the conference chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. Mark, you spoke in detail about ANPR and underwater applications, but are there maybe some other applications where these motorized lenses might be leveraged either now or maybe even in the future as the technology gets a little better?
Certainly, there are many different types of applications that need variable focus and focal length. And one other example might be a robot for checking the stock in a grocery store. In this case, the robot is going to be driving down the aisle and looking at the stock levels, and it may have a variable distance from the shelf due to some obstacles. In addition, the stock might be at the front of the shelf or the back of the shelf, and you want to have a very good image of the package. So you'll change the focus distance remotely or via an embedded computer to get the best image of that stock. And that's one example that I do know of at least a couple robot companies that are doing that type of application.
Oh,
So,
very cool. Thanks for a little bit of
mhm.
extra insight here, sticking around to answer a question. This session is hosted by us at Photonics Media, and we certainly hope everyone is enjoying the third annual Vision Spectra Conference. Thank you all so much for joining us.
Thank you.